Hi. So in the last two lectures of this course, we are going to discuss carbon-based manufacturing. So you have recently learned that carbon is used for making electrodes for battery and supercapacitor devices. You also know that we make carbon fibers which are used for making composites, and then these composites are used for making, for example, wind turbine blades. So carbon is very much related to the field of energy. So you need to know a little bit about carbon-based manufacturing. Okay. Now, what is carbon? Is carbon just one material? So as such, if you think about carbon as an element, yes, it's just one element, right? But when we use the word materials, especially when we use the word materials in the context of manufacturing, then often what happens is that based on the manufacturing, the name of the material is changed. Now, in some cases, the name is changed only slightly, but in the case of carbon, we have a wide variety of carbon materials. So, for example, if we take silicon, then we say amorphous silicon and crystalline silicon, right? But in the case of carbon, you don't just have two things, amorphous carbon, crystalline carbon. In fact, amorphous carbon, you will rather not use the term amorphous, you will use the term disordered carbon, because it's really hard to find a carbon material which is completely amorphous. It will always have some crystallinity in it. Now, the crystalline carbons are also either diamond-like or graphite-like. sp3 based carbon materials or sp2 based carbon materials. Right, so carbon, now if we talk about carbon nanomaterials, what are nanomaterials? Nanomaterials are any materials which are prepared by bottom-up processes in most cases. So you synthesize them or you do CVD, chemical vapor deposition, to manufacture them. And these are the materials where their entire size is less than 100 nanometer for each unit. Now, when we have millions of such units, then we'll get a powder, and that powder will be called the nanomaterial. That is what, if you want to buy, that is the powder that will come in a bottle. Say this is carbon nanotubes powder. So each nanotube, we have good control over its manufacture, we have good control over its properties, and we assure that these are, within 10 to 20 nanometers, whatever is the size of that. But that is for individual nano unit. Now, a lot of such individual units then make this powder. So in the bulk form, you call it carbon nanomaterial or any nanomaterial. So carbon also has a lot of these nanomaterials. And that is why sometimes, it's a good thing that we have so many materials, right? But at the same time, it also becomes very confusing. The nomenclature becomes confusing. Sometimes even when you find information on the internet, that might be wrong in many cases. And also every day the nomenclature is changing. Every day we are coming up with new carbon materials. So it is a very, very vast field and it's not so easy to learn. Okay, but what we will talk about here is the mainly sp2 bulk carbon. Why I am calling it mainly sp2? sp2 type carbon, sp2 hybridization gives you graphite, right? Or graphene. If you take a single flake of graphite, you have a layered structure, A type structural arrangement. If you take just one two-dimensional sheet, that is called graphene. It has to be, however, only one sheet, and it has to be defect-free in an ideal case. So that is one graphene sheet. Anyway, so this graphene and graphite, they are the hybridization state of the carbon atoms is sp2, but the materials that are bulk carbon materials, even bulk graphite, industrial graphite, when we talk about it, then it will not have all sp2 hybridized carbon atoms. You will also have some disordered structures, and that is why you will call them sp2 type carbon, not just graphite. Okay. So this is for us important. Why? Because this is the type of carbon which is actually used for making battery electrodes because of its electrical and electrochemical properties. And similar material is also not graphite, but sp2 type carbon material is also the one that you have in the carbon fiber. So this is what we talk about. Okay. Now this type of carbon material is hard and brittle. So you cannot really do manufacturing using the traditional manufacturing tools and techniques. Okay. So what do you do? One option is that, similar to carbon fibers, that you make whatever structure you want to make, fiber or whatever, into a polymer and then convert it into carbon via heat treatment. Why does this process really work? Because what are polymers? Polymers are mainly hydrocarbons. Now, some of them may have a a lot of carbon. Some of them may have, you know, many oxygen atoms, for example. Some of them may also be silicon-based polymers. So not all of the polymers will carbonize. Some polymers will give you very good quality carbon. By good quality, I mean good quantity also, like, you know, the fraction. Whatever material you take, do you get 30% carbon out of it or 40%? How much is the mass loss? So some polymers will give you a lot of carbon. But on the other hand, some will not give you any carbon or will give you very, very little carbon in the form of just, you know, powder. So your entire structural integrity will be lost. So you made a fiber, but after carbonization, you just got nothing, maybe some tiny particles of the carbon. Maybe sometimes the carbon is very, very porous. So depending upon the structure of the polymer, the chemical structure of the polymer, you will get different fractions and different quality of the carbon. So you have to, that is why choose certain specialized precursors. So you know that polyacrylonitrile is a well-known precursor in the case of carbon fiber fabrication. Now in the case of bulk carbon fabrication and also for making carbon-based micro nano devices, I will come to it. You have phenol formaldehyde resins, which is a class of polymers, and these are the common polymers for making small-scale structures. Okay. Now, when we do this heat treatment, we'll do it minimum to the temperature of 900 degrees up to 3000 degrees. Okay. Why? Because up to 700 degrees, what is happening in the polymer is that the non-carbon atom, the hetero atoms of that polymer and the carbon, those bonds are breaking, cleaving. So that is what is happening up to 700 degrees. Now, because of this cleavage, what happens is you will form also smaller hydrocarbons, you know, polymers will disintegrate, and then some of these smaller hydrocarbons will just go out as tar, or they will, some very small hydrocarbons will also be formed, some gases will be formed, methane will be formed. So these gases will go out as, you know, as a mixture of gases. In fact, this is what people do when they do pyrolysis for waste management. They take a lot of waste material, which is a mixture of everything. Now, a lot of these tarry and gaseous products will go out. The tars are, the mixture of tars is called pyrolysis oil, and then the gases are called synthetic gases or syn gases. Now, the third thing which you receive in pyrolysis, especially when you're doing it under the inert atmosphere, you're preventing the burning. Then the third thing that you get is your solid carbon. So when you do carbon-based manufacturing, not waste management, when you do carbon-based manufacturing, you want to maximize the fraction of this solid carbon, minimize the fraction of pyrolysis oil and the synthetic gas. Okay. So now the pyrolysis temperature, it is sometimes up to 600, 650, 700. In some polymers, it can also go slightly higher. That depends on the nature of the polymer that you're using. Okay. Now, if you keep on heating the material even further, then the carbon bonds start to form. And if you keep on heating it, as you increase the temperature, the more and more crystallinity you will get in your carbon material. Some polymers can actually give you graphite after heat treatment up to 3000 degrees. But some polymers will never give you graphite. For example, phenol formaldehyde resins, they will never give you graphitic carbon. They will always give you something which is still disordered material. So it will shatter on breaking. It will be physically amorphous. These carbons are normally known as glass-like carbons or activated carbons, depending upon their surface properties and the mechanism of carbonization. So these are the different types of carbons you can get from the heat treatment of polymers. Okay. Now you already know that you can make carbon fibers using this process. You can also get bulk carbons, you know, and you can also get micro scale devices. Now, how do you do that? So same process, you make something onto a silicon wafer for using, let's say, photolithography, and now you convert the entire thing. You put the entire chip on which you have your structures. You put the entire chip inside a furnace and heat it up to 900 or 1000 degrees. You will not go above 1400 degrees in the case of micro devices. Why? Because silicon melts at 1400, 1410. So in that case, you want to prevent it from melting, and that is why you will never use temperatures higher than 1000, 1100. Okay. So this I have already mentioned to you that some polymers are better than the other for yielding carbon. Okay. Now, I was talking about two types of, you will get graphite or you will not get graphite. Similarly, you will get sometimes a very flat and glass-like carbon. Glass-like means it has a shine like a glass, this almost reflective surface. But sometimes you will get something like charcoal, something like activated carbon, if you've heard that name. Something which has a lot of porosity in it and which is hydrophilic. So this happens because of two mechanisms, something known as coking and another one known as charring. In the case of coking, your polymer will become semi-solid or liquid also in some cases during its pyrolysis. So when it is liquid, of course it will settle down and it will have a very flat surface. So when after that you get the carbon with a very flat surface. But in the case of charring, you will not get the flat surface. You will rather get porosity in your material. So that is a difference. Okay. Now also remember that this liquid, sometimes it's just rubbery, soft, semi-solid structure, not liquid completely, but still we call it coking mechanism. Okay. Now, as I mentioned, in all cases there is mass loss. In the case of microfabrication, what do you do? As I said, so here it is with the pictures. You photolithographically pattern the structures. Typically, you will use a resist which is commercially known as SU8. This resist is based on phenol formaldehyde resins, and that is why it gives you good quality carbon. Okay, so now you put the entire structure inside a furnace and you will get, let's say if you made pillars, you will get carbon pillars. But as you can see in this image, the pillars will be smaller. They will be shrunk. Why? Because there is a lot of mass loss. Typically, you will get whatever was the mass in the beginning of the polymer. After carbonization, you will only get, let's say, 30 to 40% of that. That depends on various factors, viscosity of the polymers, molecular structure, and so on. But there is always a mass loss and there is always a shrinkage. Okay. So now, can you make these in flexible devices? We were also talking about that. Well, in some cases, you can transfer these patterns onto the flexible device. Or let's say you take a polymer, you put your structure inverted and then you remove the silicon, you peel it off. But that is very difficult because these structures will have very good adhesion to silicon. But if you intentionally somehow can make a bad adhesion, or you can make a silicon oxide layer which you can etch with hydrofluoric acid afterwards, so then in that case you can do this pattern transfer. Another option of making flexible carbon structures, polymeric carbon structures, is to use laser irradiation, where you're actually providing the heat that you would otherwise provide in a furnace. Here you're providing that heat by a laser, let's say IR laser, on top of a polymer, and then you're writing using a laser, and that's how you're getting the carbon structures. The quality of this carbon is not very good. The purity is not good, and it will have a lot of porosity because this preparation is happening, the carbonization is happening very, very fast, as opposed to the furnace treatment, where we are very slowly 2 degrees centigrade per minute. That's how we are heating the material, So all the gases that are being formed, all the non-carbon atoms that are being released, we give them enough time to release. But in the case of lasers, the process is so fast that they just abruptly release, and that is how they create a lot of pores in the material. And also the purity of such carbons is not more than 80%. So depending on the applications, whether or not you want to make laser assisted carbon, you can decide. Okay, so the last thing, as you already understand, these are the top-down manufacturing processes for making carbon structure. In the next lecture, I will be talking about bottom-up techniques, which means you take a carbon nanomaterial, which most probably is synthesized using CVD techniques, and then how do you make a device or a structure from that. This is what we'll learn in the next lecture.